We're on Unit 2, Day 3. We're on the last 2 pages here. We're going to go back to using Excel to approximate derivative values, and we're going to just merge that together with the new work we've been doing where we sketch derivative functions. So first here it says that we've been given this quadratic function, and it says go into Excel and sketch a graph of this thing from -5 to 5. So I've already created the input-output table. I'm going to insert a sketch of that. There we go. It's a parabola that opens up. Looks like it's got a vertex. There we go. It looks like it has a vertex over here a little to the right of the origin and up. So we could have solved for that, of course, but we're just sketching it real quick here. Looks something like so. For vertex occurs at x equals -b over 2a. So it's -5 over 2 times 2, which is 5/4 or 1.25. So that makes sense that it's about 1. So this x value where the vertex occurs is at 1.25. So if I were to sketch a graph of what I think the derivative looks like, I look at the shape of f. I see f is decreasing concave up right up until x equals 1 where we have a critical point. That's, 1.25. So here is 1.25 comma 0 on the derivative function. F was decreasing concave up on the left side of that. That means f prime is negative. F prime is below the x-axis, but because f is concave up, we know f prime is increasing. So it's below the x-axis but increasing. Then after the vertex, f is increasing concave up, which means f prime is above the x-axis and increasing. So here is a sketch of what I think f prime should look like. So what I want to do now is go back into Excel and refresh ourselves on how we estimate the derivative in Excel and check. We can make a graph then and see if our estimate looks like what we thought the derivative should look like. So recall, when we estimate the derivative in Excel, we are going to start at an x value. We're going to travel a little tiny bit to the right. So I go 0.000001 units to the right. So this x value, this new x value in column C, is the previous x value plus 0.000001. Drag it down, maybe adjust the column width if necessary. Then I evaluate the function. I find the y value at this new x value. So it'll equal 2 times this new x value squared minus 5 times this new x value plus 7. Drag it down. So I'm going to find the average rate of change from x equals -5 over to x is -4.999999, and then do the same at x is -4 and the same at x is -3. We're going to find these average rates of change of these points that are extremely close to each other, and that should serve as a good estimate of the instantaneous rate of change, the f prime value. So we do a change in y over change in x. Don't forget parentheses. So we put parentheses around the change in y, y2 minus y1, divided by parentheses around the change in x, x2 minus x1, and drag it down. Again, adjust your column width and you'll see approximately the derivative here is -25, approximately -21, approximately -17. These are giving good estimates of the exact derivative values, which tomorrow in our next video we're going to actually see it is -25, it is -21. So for now, what I want to do is just create a little sketch of the derivative. So I'm going to highlight the x values here. I'm going to hold down Control and highlight the y values of the derivative. And then I'm going to insert a graph. And there it is. It's increasing, looks like a straight line, just like our sketch looked like a straight line for the derivative. Looks like it's intersecting at 1.25. That makes sense. Looks like a pretty good graph for what we thought it was going to be.